Hi guys, this is Mrs. Rooker. Welcome to Unit 2. Today we are going to be reviewing radicals and exponents. So the first thing I want you to do is pause the video and try and do number 1 and 2, the review problems. And then unpause the video and I'll go over those. Alright, so now I'm going to go over them. Remember, number 1 is a quadratic. We can see here that there's an x squared, which means that it's a quadratic, which makes the parabola shape, which is a U shape. So the number in front here, which is a -1 technically, tells us that it is going to be a parabola pointing downward. And this is also in vertex form. And our vertex, actually I'm going to rewrite this, it's going to be -x plus 0 squared, because there's nothing else that's being squared with the x. So I'm going to put a plus 0 and then just keep this plus 5 hanging out on the end, so I can really tell that it's written in vertex form now. And to find the vertex, we do opposite of this number here and the same as this number here. So the opposite of 0 is still just 0, and the opposite of 5, the same as 5. So the vertex is 0, 5, and it's a parabola pointing down. So I'll do a rough sketch of this. 0, 5 is the vertex, and it's pointing downward. Domain is how far left and right the graph goes. So these arrows tell us that it goes forever to the left and also forever to the right, which means it's -infinity to +infinity for the domain, which could also be written as all real numbers. The range is determined by how far up and down it goes. So I always start with how far down it goes. So it goes down forever, so that's -infinity, because it goes down forever. But then it only goes up to here. That's as high as it goes. It never goes past 5. So 5 is as high as it goes. This can also be written as x, not x, y, because we're talking about up and down. We're talking about range, which is y values. Y is less than or equal to 5 because it never goes above 5. All right, so that's the answer on number 1. Number 2, we're supposed to find the slope-intercept form of a line that goes through those 2 points. To find the slope-intercept form, I am first going to find the slope. Sorry, my pen's not working very well. To find the slope, I do m equals y2 minus y1 over x2 minus x1, where this is x1, y1, x2, y2. And remember, it doesn't matter which one's the first point and which one's the second point. I just chose the one that was written first to be the first point. All right, so y2 is -11 minus y1, which is 4, over x2, which is 8, minus x1, which is 3, equals -15 over 5. Reduce that, I get -3. So the slope is -3. That's my m. And then I'm just going to plug into y equals mx plus b to find what the b is going to be. So y equals mx plus b, which is slope-intercept form. Y equals mx plus b. I know the m. The m is -3. So m is -3. But I don't know the b, so I can't just write it in slope-intercept form yet. I do know an x and a y, though. I'm just going to pick this point. It doesn't matter which one, but this one looks easier. And I'm going to plug 3 in for the x and 4 in for the y. Oops, 4 in for the y. So I just plugged into y equals mx plus b. I replaced the y with 4, because that was a y value on this point. I replaced m with -3, and I replaced the x in y equals mx plus b with the 3 in that first coordinate point. I could have done -11 for the y and 8 for the x, but 3, 4 seemed easier to me. And then I just simplify this. I multiply -3 times 3, I get -9. So 4 equals -9 plus b. And then to get b by itself, I add 9 to both sides. I believe that's 13 equals b. So b equals 13. Now I have m, which is -3, and b, which is 13. You also could have done the same thing by finding the slope, like we did, and then plugging into point slope form, and then simplifying. Okay, so now what I'm going to have you do is look at this box, and I want you to fill out or write down all of the perfect squares that you know, all the way up to 15. So basically fill out the perfect squares in this box, and then actually not all the way up to 15, all the way up to 20 squared. And then do the same thing with the cubes. I would actually take this a step further and also do 6 to the third power and 7 to the third power. Maybe even 8, 9, all the way up to 10 maybe. The more you have memorized, the easier some of these problems this unit are going to be. So pause the video right now, write down all the perfect squares, and then unpause and I'll go over it all. Okay, so here are all of the perfect squares and perfect cubes. I decided to go to 10 with the perfect cubes. So yeah, I would pause the video, make sure to have these all correct. If you don't have them all correct already, pause and rewrite them. And then try to memorize as many of these as you can. It's not necessarily a requirement, but it will make your life a whole lot easier if you have them memorized. If you don't have them memorized, you can always guess and check, but it will take a lot longer. Right, so now we are just going to review square roots and cube roots. So remember, this symbol is called a radical. It's also referred to as a square root. If it is not written, if there's nothing written here, we assume that there is a little invisible 2 here, which means that this is a square root. That little invisible 2 there is called the index. Like here is on number 5. Oops, my pen's not working. There we go. On number 5, the index is 3. If it's not written, the index is 2, meaning square root for this one, cube root for number 5. So again, like I said, that's called the index. If it's not written, we assume the index is 2. What an index of 2 means is we're trying to find the number that multiplies by itself, so 2 times, to give us 64, which is just backward from what we were doing here. So if we look here, 8 squared was 64, which means 8 times 8 is 64. So the square root of 64 is just 8. Right, moving on to the next one. What multiplies by itself 2 times to give you 36? 6 times 6 is 36, so the answer here is 6, but there was a negative in front. That negative in front just stays as it was. We weren't taking the square root of the negative because the negative was on the outside, so it just stays as is. All right, it's the same deal on the next one. The plus or minus stays in front, and then square root of 49 is just 7. All right, next one's different because the negative is under the radical, which means I'm taking the square root of -4. But nothing multiplies by itself to give us a negative, because a negative times a negative is a positive, and a positive times positive is also a positive. So this is actually impossible, which means we take the square root of 4, which is 2, but we can't take the square root of a negative, so we put I there, which stands for imaginary. You'll always get an imaginary solution when you have the square root of a negative. Next one, cube root of 64. What multiplies by itself 3 times to give you 64? That's not 8, because that would be the square root of 64. This is going to be 4, because 4 times 4 times 4, 3 times, gives us 64. The next one, a lot of people think the answer is going to be 3i. That is not the case, because this isn't impossible. You can find a number that multiplies by itself 3 times to give you 27, because negative 3 times negative 3 times negative 3 is negative 27. So negative 3 is the cube root of 27. Cube roots of negatives are possible. Square roots are not possible. I am going to have you guys do the next one on your own. Pause the video and I'll put the answer up there. So that should be the correct answer for number 7. On number 8, the way I like to do these ones is to remember what the index is. That's 2. And then I just like to determine how many times does 2 go into 4. How many times does the index go into the exponent? 2 goes into 4 2 times, which means b squared is going to be our answer. Because b squared times b squared will give us b to the 4th. Same deal on the next one. How many times does 3 go into 3? 1 time. So g to the 1st is our answer, which is just g. Feel free to pause the video at any time if I'm going too fast. This is a fairly long note, so I have to go pretty quickly. 3 goes into 9 3 times, which means w to the 3rd is our answer. W to the 3rd times w to the 3rd times w to the 3rd will give us w to the 9th. Right. Moving on to the next section. Approximate the value of the radical by listing the 2 integers that it lies between. Integer means whole number, so we're trying to find the 2 whole numbers that are closest to root 18. The way I do this is I think of my perfect squares. So this list over here, think of all my perfect squares and think about the ones that are closest to 18. You can see here that those 2 are closest to 18. So square root of 16 and square root of 25. But those aren't integers. We're going to reduce those. Square root of 16 is 4. Square root of 25 is 5. Those are the 2 integers that 18 is closest to. If you actually type root 18 into the calculator, you get something like 4.2 something, which is between 4 and 5. All right, the next one, cube root of 36. The perfect cubes that are closest to 36 are cube root of 27 and cube root of 64. Reduce both of those, we get 3 and 4. The next 2, it's the same thing except it's saying to just find the nearest 1 integer, so you don't need to do 2 numbers, just 1. So the closest perfect square to 23 is 25. Oops, keep doing that. Square root of 25 is 5. And then you also need to find the closest cube root to 100. So I'll let you guys do that one on your own. Pause the video if you need to. And then I'll move on to the next problems. I have to go quick because we have a lot to get through, and I want to keep it close to 20 minutes. All right, evaluate the following expression if x equals 64. So all that means is anytime we see an x, we replace it with 64. So on this one, I'm replacing this with 64. Everything else stays the same though. We always want to reduce the radical first, or anything under the radical first. So I'm going to reduce 64, which is going to give me 8. But I still have the 5. Since these were right next to each other, that means we were multiplying them. 5 times 8 is 40. Pause the video really quick and do the next one on your own, and when you come back, you'll see the answer. Here's the solution. Remember, you need to reduce the radical first before you can combine with something that was outside of the radical. All right, so let's move on to simplifying radicals. To do this, well, there's a couple different ways you can do this. When we teach this to Algebra 1 students, we usually teach it by having them make a factor tree and just break down 12. So any two numbers that go into 12, I would say 4 and 3. And then keep breaking down non-prime numbers. So 4 breaks into 2 and 2. That's a pair. We usually teach it that this little radical is like a jail, and the goal is to get out of jail. The way to get out of jail is to find a buddy or a partner that's exactly the same number as you. And then one of the numbers is a diversion. He distracts the guard, gets killed, and then the other guy gets to escape. This guy here, 3, didn't have a buddy, so he didn't even bother trying to escape, so he stayed in. The 4 doesn't count because the 4 broke into 2 and 2, so we no longer worry about him. So that's kind of how we teach it to Algebra 1 students. The other way to think about this is the goal is to take perfect squares out of the radical. So the other way to think about it is to break this into, find the biggest perfect square that goes into 12, which is 4. This breaks into 4 times 3. And then 4 is the perfect square, so you can square root 4 and bring it out of the radical. Anything that wasn't a perfect square has to stay in. Okay, moving on to the next one. That same kind of idea applies here. So I'm going to do kind of a combination of those two methods. So I'm going to break this into a factor tree, but I'm going to look at this and try to find perfect squares. I don't want to do 6 and 3 because there's no perfect squares there. I would rather do 9 and 2 because 9's a nice big perfect square. The square root of 9 is 3, so that means 3 gets to come out. 2 wasn't a perfect square, so 2 stays in. This would be the same as if you kept breaking down 9. Then a 3 comes out, 2 stays in. All right. Next one. I'm going to use that same method. I'm going to think about all my perfect squares. I know that 9 goes into 72, but I think I can do better than that. I know the next perfect square after 9 would be 16. That doesn't go in. So then 25. 25 doesn't go into 72. My next perfect square is 36. 36 does go into 72. This breaks into 36 and 2. Which I like because 36 is a nice big perfect square. The square root of 36 is 6, so 6 comes out and 2 stays in. I could have broken it down further. I could have broken it down a different way, but this saves us a lot of time if we do big perfect squares. All right. Next one, 48. Think of your perfect squares. 4 goes into it, but we can do better than 4. 9 doesn't go into it. The next perfect square would be 16. 16 does go into 48. This breaks into 16 and 3. 16 times 3 is 48. So square root of 16 gets to come out. So square root of 16 is 4. And the 3 stays in. Notice I left room because I'm going to break down the b. So I'm going to do the same thing that I did up here. Where is it? I don't want to scroll up too far. I'll lose where I am. The same thing I did before where I think about how many times the index goes into the exponent. So 2 goes into 3 one time, which means 1b gets to come out. But there was 1 left over when 2 goes into 3. So that means 1b has to stay in. So my answer is going to be 4b root 3b. All right, just a few more. Let's try the next one. Think about your perfect squares. 4. 4 doesn't go into 54. Next perfect square is 9. 9 does go into 54, but you might want to keep going and see if any higher ones do, because the bigger the perfect square, the better. 16 doesn't go in, 25 doesn't go in, 36 doesn't go in, 49 doesn't go in, so 9 must be the highest. So this breaks into 9 times 6. Square root of 9 is 3, so 3 comes out, and the 6 has to stay in. So 3 came out, 6 stays in. And then I look here, the index was 2, even though it wasn't written. 2 goes into 2 one time, which means 1x gets to come out. All right, next one. You could break this down, and it would take a long time probably. Or if you have your list of perfect squares memorized, you will know that 18 squared is 324. Sorry, yeah, 324, which means the square root of 324 is just 18. Moving on to the next one, cube root. So when you're trying to find the cube root of something and you're breaking them down, you don't just need pairs, you need groups of 3. Or if you're doing it the method that I've been talking about, you need perfect cubes. So I'm just going to break this down, but I'm also going to kind of have in the back of my mind that I'm looking for perfect cubes. I know 1 times 1 times 1 is 1, that doesn't really count. 2 times 2 times 2 is 8. 8 does go into 40. 8 times 5. 8's a perfect cube, so I know that this can break into 2, 2, and 2. So 2 comes out, the 5 must stay in. Don't forget the index on the outside. If you don't write that, then you're wrong. 2 root 5 is not the same as 2 cube root 5. All right, last one. Sorry this video went a little over. Try this one on your own really quick. So pause the video, try this on your own, and then unpause, and I'll go over it. So for perfect cubes for 72, 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 would be 64. So 72 doesn't have a lot of options for perfect cubes, but I do know that 8 goes into it, which is a perfect cube. So that's going to be 8 times 9. 8 breaks into 2, 2, and 2. So 2 gets to come out. 9 stays in, because there aren't any other perfect cubes that go into 9. So we know that that's fully reduced. And then the last thing, how many times does 3 go into 7? 3 goes into 7 twice. So that's going to be y squared that comes out. But there's 1 left over when 3 goes into 7, because 3 times 2 is 6. So there's 1 left over when 3 goes into 7. So 1y has to stay in. And that should be your answer. That's it for this lesson. Make sure to come to class with questions, or yeah. All right, have a good one, guys. Thank you.